Okay, so now we're going to look at probably what is even a more important concept known as linear independence. And here we've got our definition for what this is going to be. It says a set of vectors, v1 through vp, is said to be linearly independent if and only if, that's what this IFF means, if and only if, the only solution to the equation that's shown here, x1, v1 plus all the way through xp, vp, is equal to the zero vector. This represents the zero vector. So if the only solution to that homogeneous equation is the trivial one, then the set of vectors is said to be linearly independent. So more simply, really, what we're saying here is if the solution to the homogeneous system has only the trivial solution, the set of vectors is linearly independent. If there are infinitely many solutions, then the set is linearly dependent, and we can write at least one of the vectors in terms of the others. This is really what it comes down to in the end, is as I'm looking at each one of these vectors that are in the set, what we would like to know is whether or not they're all independent from each other. In other words, could I write, say, v2 in terms of, or as a linear combination of, all the other vectors in the set? If I can do that, then that vector is redundant. I don't need it in my set. And so we would say that that set is linearly dependent. We could pull it out and make sure that there's no other redundant vectors in there, and then we're back to a linearly independent set. This is something that we'll be doing as we go forward. So understanding the concept of linear independence is pretty essential for us as we move on through the course. So we want to make sure we get a good understanding for what this is saying. So here's an example to try and illustrate how we can show this and what exactly it means. So let's determine if the set of vectors is linearly independent or dependent, which is the alternative. If they're not linearly independent, then they're dependent. So let's see what we get. So we'll take v1 to be equal to the vector 1, 2, 3. And we'll take v2 to be equal to the vector 2, negative 1, 4. And we'll take v3 to be equal to the vector 0, 5, 2. So here's our three vectors, and we want to know whether or not these three vectors are linearly independent from each other. Again, the idea is, could you write one of these vectors in terms of, or as a linear combination of, maybe the other two that are shown? And that's what we have to try and establish. So we're going to set it up as a homogeneous system and try and determine whether or not we get only the trivial solution to that system. So let's just throw it all into a matrix. And here's our homogeneous system, remembering that that's when we just set all of these things equal to 0. At this point, we just have to row ref it and see what happens by plugging that into Octave or something and asking it to row ref that particular matrix. And we would get a particular result. I've already done that and converted this back into variable equations, and we end up with x1 being equal to minus 2x3, x2 being equal to x3, and x3 being a free variable in that case. So what we have now is that the set is linearly dependent, because we got more than just the trivial solution out of this. In fact, we get infinitely many solutions. So that means that one of these three vectors can be written in terms of the other vector. The next step would be to figure out exactly what that looks like. How in the world would I write one of these vectors in terms of the other two? Do that by example. And let's go ahead and take x3 equal to 1 And that implies that x1 is equal to -2 and x2 is equal to 1. And using that as a linear combination with the homogeneous solution, we would have that -2 times v1 plus v2 plus v3 equals the 0 vector. Or if we just rearrange this a little bit, we could solve it maybe for v3 and say that then v3 is going to be equal to 2 times vector 1 minus vector 2. And if you look, so here's our statement. What we're saying is that vector 3 is equal to 2 times vector 1 minus vector 2. If we go back up to our original vectors up above here, you can now verify that in fact that's true. And that's what makes this set linearly dependent. Again, I can write that vector 3 in terms of vector 1 and vector 2. So as far as I'm concerned, it's a redundant vector in my set, and I don't need it. And that'll be something that we work on later on that's called a basis. And again, that's a super important concept. For now, we're just trying to figure out whether or not sets are linearly independent or dependent, which amounts to taking the vectors, putting them into a matrix with the 0 vector on the other side of the augmented matrix, and just row refing it and see the trivial solution. It's linearly independent. If you get infinitely many solutions, it's linearly dependent, which means that you can write one of those vectors in terms of the other two, or the other vectors that are present. And oftentimes I will ask to have students work through that process to solve all the way down to here if in fact it is linearly dependent. So do be prepared to do that. Sometimes we can classify a set of vectors as linearly dependent without solving the homogeneous system. And there is a theorem here that we'll draw on that will help us with that. So let's just look at that. This is going to be theorem 11 in your text. So let's let V1 to VP be a set of vectors here. In Rm. So the m-dimensional space. Then what we get out of this, it says if P is bigger than M, so if I have more vectors than the size of the space, then the set is automatically linearly dependent. And here's a quick example for that as well. It's not a terribly difficult concept to get, but sometimes reading the statement makes it more complicated than it really is. So we'll take V1, V2, and V3 here. I'll take 3 vectors. And that's a 5. So I've got 3 vectors here. The size of this space is actually in R2. These are 2-dimensional vectors. Each one of these has 2 components to it. So we're in R2. So I have more vectors than the size of the space. I have 3 vectors in R2. So automatically it's going to be linearly dependent. Anytime you have more vectors than the size of the space, then you're going to have a linearly dependent set. So if I have 4 vectors in R2, it's automatically linearly dependent. If I have 5 vectors in R4, it's automatically linearly dependent. And we'll explore that a lot more as we go through the ideas of linearly independent and dependent. We'll find new ways to show that a set is linearly independent and dependent, and further that discussion at that point. So here's a couple of examples below where you can sort of practice some of these concepts and see how you do with it.